All right, ladies and gentlemen, this class recording has started. Much to the chagrin of all of the other people who would watch this recording, they didn't get to hear that little, pre-show, like little pregame. It's like the lower bill comedian that comes out and Anyway, the end of section 5.1 deals with Newton's third law. So over the past week, we've talked about Newton's first two laws. First, Newton 1. One word to summarize Newton's first law, and that is inertia. Things not changing or things staying the same. Newton's second law, we said, can summarize in one word as well. If Newton's first law deals with things not changing, acceleration, right? So Newton's second law deals with acceleration. We talked about that two factors affect the acceleration of an object. What are those two factors? Net force and mass. Okay? All right. Newton's third law gets summarized in two words. And those two words are action, reaction. Okay? So, to start that off, demonstration. Up on the track in the front of the room, I have two carts. And each one of those carts has one silver bar in it. Okay? So, we've used the carts before, right? And the red cart, I pushed in the little plunger, right? And it shoots out when I hit the button. Okay? So, I'm going to put the plunger back into the red car, put them next to each other, and then I'm going to push the button on the red car, and this happens. Take two. All the poor people watching the recording are going to be like, "What happened?" Don't worry, only like a few people are bleeding. That's all. So
Batman came in and hit the red.
Yes. All right. Take two. So red car, blue car, right? We set them off. Okay. So there was only one plunger at work. The plunger shoots out of the red car, applies a force to the blue car. And as a result, the blue car starts moving. But what else did we see happen? Red car moved as well. Which way? Opposite way. How fast did it move? The same speed, right? Because they both hit the blocks at the end at approximately the same time. The only way that red car goes from sitting still to moving is if what? Net force acts on it, right? So even though it appeared that red applied a force to blue, well, I guess we shouldn't say make that assumption, even though it appears that red applied a force to blue, red also had to experience some kind of force because it started moving as well. The only thing that it interacted with was blue, therefore we can sort of come to the conclusion that red pushed on blue, but blue also pushed on red, even though, according to the setup, red was pushing blue. Right? Does that make sense? So, Newton's third law describes interactions between between objects, and those interactions are forces. So, the first heading, right, underneath Newton's third law, says that forces always come in pairs. We never find a single force isolated in the universe. Forces always come in pairs. In the case of the example that we just did, red pushed on blue, but automatically blue pushed back on red, because forces never happen alone. Right? That leads us to the two key points that go along with Newton's third law. The first one being, let me zoom this up here. The first one being, for every action force acting on an object, there is a reaction force acting on a different object. So that's where the action-reaction comes in. Red pushes on blue, blue pushes on red. Okay? Then the second key point says the action and reaction forces are equal in magnitude and opposite in direction. We saw here, right, that when red pushed on blue, red and blue both ended up hitting the block at the end of the track at exactly the same time. So we said that that means, oh, they must have experienced the same force in order to experience the same acceleration. Good with that, right? I've added a second silver bar to the red car, right? Again, put this in, two cars together, right? If I set them off now, what should we see happen? Go ahead, Brett. Blue one will go faster. Will red move? Yes, but not as fast, with less what? Acceleration. Okay? Right? However, does that mean that red experienced a different amount of force? Same force, but the acceleration an object feels isn't solely responsible from the force. We also have to play in the mass. A greater mass on the red means a smaller acceleration. Okay? Good there. All right. Now we have to go ahead, Red. Let's take that. Okay? So, yes. Okay. What? Very nice. All right. So, Brett, that's one of the first misconceptions that we have to take care of. Okay? So, Brett said we could make it heavy enough that it doesn't move, right? For instance, if I do this, ready? Well, pretty much, yeah. So, in case you were watching the video, I just jumped up in the air. It was like a good 40-inch vertical. I mean, it was like I basically hit my head on the ceiling. So, you know, just picture that if you're watching the video. So, okay. All right. But in order for me to jump, to accelerate upward, I have to experience a force. In which direction? Upward direction, because that's the way my acceleration is. Okay? But that force is coming from the ground. However, the ground only applies a force to me if I apply a force to it. Action, reaction. I push on the ground, it pushes on me. I go up. What happens to the ground? Really? Okay, so does the ground experience a force? Sure, it has to. Newton's third law, forces come in pairs. Does the earth accelerate? Yes. Okay. Remember, forces determine if something accelerates. Okay? Forces cause acceleration. Specifically, net force causes acceleration, right? So if I push on the ground, as long as there's nothing pushing back up on it on the other side, there is an unbalanced force. Force is responsible for determining if acceleration occurs. But what determines how much acceleration there will be? Mass, right? Specifically, Simran, what kind of relationship do mass and acceleration have? Inverse relationship. Just like the two cars, trial 2, we increased the mass of the red car, right? It experienced a force, but it didn't experience as much acceleration because it had a greater mass. Forces don't determine if something accelerates. Sorry. Forces determine if something accelerates, not how much. So, Brett, to answer your question, could we make red heavy enough that it wouldn't accelerate? No. Could we make red heavy enough that it would accelerate a very, very, very small amount? Yes. Ready? All right. forward. You apply a force to the ground. You push it, it pushes you. You go forward, what has to happen to the earth? It has to go backwards or down, depending on whether you jump or step, right? But how much does it accelerate? Not very much at all, because the mass of the earth is so very large. Okay? So even if in a situation like that, right, remember, the forces, right, both objects experience a force. Even though it may seem that only one object is moving, that's not really saying that the other object doesn't experience a force. It does, but its acceleration is so small because the mass is so big. Okay? Good there? Okay, so then how does that apply in space? In space, right, another thing that we have to consider as well is that the motion, whether an object moves or not, is determined not by force, but by net force, right? So, I throw the ball. It's been a great recording day. Alright, so I throw the ball, right? Okay, so first, I throw the ball. I apply a force to it forwards. What has to happen? It has to push me backwards. But do I go anywhere? No. Is that because my mass is so much bigger than the ball? No. Is this ball the only force that is acting on me? Not gravity. That's not my gravity dance. There is friction between my feet and the ground. Okay, so that is a friction dance. For the rest of the year, remember that. So, use stick figures to demonstrate friction dance. You'd have to draw like a three picture sequence. So, yeah, arms this way, then arms this way. You gotta do the feet too. So you gotta make sure the feet are. Poor people on the recording will never know. They're gonna fail. But I don't accelerate in that circumstance, not because the ball doesn't push back on me, or not because my mass is so much greater than the ball, but the ball is not the only force acting on me. There's also friction. Those forces cancel. Okay? But in space, there is no friction. So if I threw the ball this way, what would start happening to me? I'd go backwards. How fast? Would I go back as fast as the ball? No, right? We experience the same force, but the acceleration that we experience is also determined by our mass. So the ball would go faster than me for the same reason that the that the blue car went slower or faster than the red car. Okay? If we can isolate those action-reaction forces, right, then we can see them. So, in space, right, spaceships, you guys are only talking about this before, right? Spaceships don't work like airplanes. Okay? Airplanes rely on the air to help them steer and to help them brake. But there's no air in space. Right? No, you can. You just have to drive them differently than airplanes. Okay? So, to maneuver a spacecraft, because we maneuver spacecraft all the time, right? Satellites go up and they dock with the International Space Station and stuff like that. That happens all the time. Okay? They don't just get all the calculations right the first time and it just eventually they run into each other. They have to maneuver a little bit. Or you ever see Apollo 13? Anybody ever see Apollo 13? It's on like USA like every 3 weeks, like 4 times over the weekend, so anyway. But there's that one part where they have to manually fire the engines, right? And they have to keep the moon in the window, and stuff like that, right? That's how they maneuver. So, in the case of maneuvering a spaceship, if you want to turn right, okay, you have to first apply a force this way, so the opposite force goes that way. Right. Okay. Or, again, yes, exactly like Wall-E. Okay. You ever seen Wall-E before?
Yeah, I have.
You know the part where he's dancing outside the ship with the fire extinguisher? It's
yeah.
actually a really great example. So, you know, I've used that before as an example in class, so we've actually watched it in class.
I'm just Mrs. Lipsky though, did a really good job.
So,
explaining it.
all right. So yeah, exactly like that scene in Wall-E. Like that, you know, if he's traveling this way, right? He's traveling to the right, but wants to slow down, right? He has to actually apply a force, or shoot the fire extinguisher to the right, so it applies a force back to him on the left, right? If you're going in a certain direction, the reaction has to go in the opposite direction, right? So you would fire the fire extinguisher in the direction that you're going, so it pushes back on you and slows you down. Right? That makes sense? Right? Good. Now, the problem with that is, right, that because the Earth is a sphere, right, it gets forces from all directions. So the question that comes up with the example that I did last time is, if we all jump, if everybody on the Earth jumped at the same time, would be able to knock the Earth out of the orbit? And the answer is no, because we're all on different sides. So those forces would cancel, right? So the answer to that is no, because there are 7 billion people on the Earth, right? No. Listen. No. Even if we got everybody, like let's say we all met in Australia or something, right? Now, all the people on the Earth go to Australia, right? Okay. There are 7 billion people on the Earth, right? 9 zeros, right? Let's say that each one of them, in order to jump, applies even if it's 100 newtons. Okay, let's say that. We could actually figure it out. We could do some calculations to figure it out. But let's say, to make it easy, it's 100 newtons. So that's 70 billion newtons. 9 zeros. Wait. 10 zeros. The billion is 9 zeros. 10 zeros, right? The mass of the Earth is 10 to the 24th kilograms. 24 zeros. So even if we had 10 zeros worth of force, 24 zeros worth of mass still makes it basically that might be a different story. Yeah. Sorry, go ahead. Maybe, although we still run into the same point that now not even 7 billion people are all pushing in the same direction. So even if there's 4 billion people pushing in one way and 3 billion in the other way, that's only a net force of 1 billion, right? So now instead of 7 with 9 zeros, there's only 1 with 9 zeros, so that's not as much, right? Go ahead. No, because I shouldn't say that, but we have like resource problems before we got to that point, like supporting that many people. So. All right, there's one last thing that we need to talk about. If you have read these key points, the second key point, the action and reaction forces are equal in magnitude and opposite in direction, might present a problem to you. If you still feel inclined, or if you feel so inclined. Anybody? Based on what we've talked about over the last week, if we have forces that are equal in magnitude but opposite in direction, what does the net force turn out to be, Krista? 0, right? So people that don't think about it critically enough read that and go, well, wait a minute, that can't be true. Because if forces are equal in magnitude and opposite in direction, they cancel each other out, net force is 0, nothing would ever move, physics is a lie, We didn't land on the moon, right? Like, okay. So, and even if we did land on the moon, terrorists would bomb the moon and send a piece to Washington, D.C., right? Anyway. But the important thing we have to remember there is where we started with this. Red applies a force to blue, and blue applies a force to red. They are not on the same object. One force, the action force, is on the blue car. The reaction force is on the red car. Two forces that aren't on the same object can't cancel each other out, right? When I did the ball throwing demonstration, I threw the ball, it pushed back on me. Those two forces didn't cancel because one force is on the ball and one force is on me. But the force of the ball on me plus the force of friction between me and the floor, those canceled because those were both acting on me. Does that make sense? Okay. Go ahead.
What if you're in space that you push this other jet? What is that like?
That's the reaction, right? Basically, in space, a maneuvering jet in space is basically a fire extinguisher, like in WALL-E. It's compressed air, and we let the compressed air out, and it pushes on us this way, and so it goes that way, and it pushes us this way.
So
It's basically like a fire extinguisher in WALL-E.
that is the action.
Yes, the action pushes on you and makes you go this way, but as a result, it goes out the other end.
So
Right.
The exhaust.
Yep. The exhaust is the reaction.
Reaction.
Yeah. Right. Yeah. That's like, you know, if this is, you know,
It's like I was thinking it's just like one object in space.
but it's not. It's the compressed gas and the spacecraft. Right? Good there. There is a short homework assignment on the calendar. It's mostly conceptual problems, but there are a couple of examples that we didn't get to in class, although they're really just F equals MA calculations, where F is the same on both objects, but one positive and one negative. So, put that up here. And there it is. So, I will see you guys next week, and we'll get into section 5.2, and we'll start applying Newton's laws to different situations. All right?